The beginning of the 1900s, so over a century ago, was a very active time in both physics and chemistry, and the two areas blended together fairly frequently. And a lot of the theories, actually, in atomic theory, tie to both sciences. And these revelations in physics and chemistry were dealing primarily with light. So in the early 1900s, there were two groups of thought on how light was transmitted. One group thought that light was transmitted as waves. The other group thought light was transmitted as particles. The group that championed light being transmitted as waves said, well, light's energy. Energy has no mass. The group that explained light as being transmitted as particles dealt with the fact that, well, okay, particles have mass, particles are matter, so somehow light and matter are tied together. They had a harder time because there still was agreement that energy and matter were separate. So the group that said light was transmitted as particles had this difficult time trying to figure out how those two things could work. This is leading up to our next school of thought. One of the big guns during this time was Max Planck, and Max Planck argued that energy, any kind of electromagnetic radiation, was transferred in discrete bundles, not in a continuous stream. So he was one of the particle people. And he said that energy was proportional to the frequency of the radiation. So if I had high frequency electromagnetic radiation, I had a lot of energy, and the frequency was how often these bundles of particles were being shot through the atmosphere, shot through space. He came up with an equation to show this relationship. E for energy equals h times nu, or h times f, would be another way to write it. You may have seen it that way. H is Planck's constant. He came up with it. And the value is 6.626 or 6.63 times 10 to the negative 34 is joule seconds. That's joules times seconds per particle. So each bundle or particle of energy is what we're looking at here. He said that energy was quantized or bundled into packets, and these packets were called photons. So the photon is the package. So different energies of light produced equals some whole number multiple of the product h nu. So the energy, the total amount of energy produced equals that n whole number multiple times h nu. N would be the number of particles. So if we take the equation that we've seen before, energy of a photon equals hc over lambda, because we've seen that wavelength and c, the speed of electromagnetic radiation, are related to frequency, we're simply taking this equation and rewriting it in terms of wavelength and in terms of c. So we have the relationship hc over lambda equals h nu, and both of them represent the energy of a photon, or the energy of a particle that's being sent through the atmosphere. Okay, Einstein was also one of the big guns during this time. He developed a slightly different relationship between the two, energy and matter. His equation that ended up getting him a Nobel Prize. He said that energy is equal to the mass of those photons times the speed of the electromagnetic radiation. So he was relating energy transmitted to the mass of those photons. So there was a question that evolved. Since one group said that light traveled as waves, another group said light travels as particles, we have this dual nature of light: particle properties, wave properties. Particle properties would be the photoelectric effect and the fact that you could get photons to bounce off of things. Matter bounces. They weren't sure about waves. So primarily the photoelectric effect was evidence of the particle nature of light. Waves, because they had frequencies, and waves have frequencies, as do sound and water waves, that was the wave nature of light. And it turns out that it depends on what you're doing and how you're studying light as to which characters of light are dominant. If we look at energy as a wave, we would tend to represent it as a traditional sine wave. So there's a sine wave. If we represent energy as particles, then we've got a series of particles here. Essentially, though, what we're looking at is a compression wave as energy is traveling as particles, because where the particles are densely grouped, that corresponds to the crest of a sine wave, and the region where the dots, the particles, are spread out, that corresponds actually to the trough of a sine wave. And so you see this alternating dense and sparse region of particles as it's being transmitted as particles, and it actually is also being transmitted as a wave. It's just as a compression wave now. So there's arguing, there was discussion back and forth, and finally they agreed that yes, energy can be both wave and particle. It depends on how you look at it. So then the subsequent question would be, okay, what about matter? Is there a dual nature to matter? Matter's been particles. Matter just sits there. This brought up the question, can matter have wave-like properties? Mr. Du Bois said yes, it can. And he used Einstein's equation and the equations linking energy and frequency, energy and wavelength together, and said that the energy of the photon equals its mass times c squared. That also equals Planck's constant times c times the wavelength of this energy wave. And so he wrote the equation so that we have it in terms of the mass of the particles and their wavelength. So the photon mass equals Planck's constant divided by the wavelength and the speed of the radiation. We can take this mass equals h divided by wavelength and c and rewrite it. And we're going to use in this case v. Here this is v for velocity. And the reason we're going to use velocity rather than c is particles can't travel at the same speed as energy. They can get close, but they can't travel at 3.0 times 10 to the 8th meters per second. So we can't use c anymore. We have to use v. So it's the same equation, same type of variable. It's just that it's not c anymore. It's not a specific constant value. So the size of the particle determines whether or not the particles behave mostly like particles or whether they can have some wave characteristics. If I have really large particles, they behave always as matter, always as particles. Can't ever have them have or exhibit readily seen wave properties. And large particles are considered molecules. Small particles can behave as waves, can also behave as particles. Small particles would be considered photons. Photons are incredibly tiny. And that leaves the intermediate particles. What's in between? Well, believe it or not, electrons are considered intermediate particles. So electrons can have matter characteristics. They are particles. They can also have wave characteristics. And this is going to be fairly important to us as we continue to discuss various parts of this chapter.